Now in this lecture we'll find out the distance between the centers of two circles. In the drawing we have rectangle ABCD. Inside this rectangle we have two circles. The center of this circle is here at point Q. The center of this circle is here at point P. Our mission is to find out the distance between the centers of those two circles, that is to say, the length of line segment QP. And we also know that side AB of the rectangle is equal to 7 units in its length, and side BC equals to 24 units in its length. According to the rule that the opposite sides of a rectangle are equal to each other, we get that side AB equals to side CD, but AB equals to 7, therefore BC must be also equal to 7 units in its length. Now, likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, here side BC equal to side AD in the rectangle ABCD. But BC equals to 24 units in its length, therefore AC must be also equal to 24 units in its length. Because of the fact that ABCD is a rectangle, it means that all the four angles inside the rectangle must be a right angle, so this angle equals to 90 degrees. This angle equals to 90 degrees. This angle also equals to 90 degrees. And finally, this angle is also equal to 90 degrees in its size. In the next step, we will focus on the right triangle ABC. And we will implement the Pythagoras theorem on this right triangle ABC. By PT is a relation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse of the right triangle ABC is AC, therefore the square of the hypotenuse is AC squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to AB squared plus BC squared. Repeat again. According to the Pythagoras theorem, the right triangle ABC, AC squared equals to AB squared plus BC squared. So AC squared equals to AB squared. AB is 7, therefore AB squared is 7 squared, it is 49, plus BC squared. BC is 24 according to what is given in the equation. Therefore BC squared is 24 squared, that is 576. In conclusion, we found out that AC squared equals to 49 plus 576, that is actually 625. So AC squared equals to 625. We take a root out of this equation, and finally we get that AC equals to the square root of 625, that is 25. So we found out that the hypotenuse AC of the right triangle ABC is equal to 25 units in its length. What is the radius of each circle? In order to find out, each circle here is blocked by a right triangle. This circle with the center P is blocked by the right triangle ABC, and this circle that is center is Q is also blocked by this right triangle ACD. And so here we'll find out a general formula for a radius of a circle that is blocked by right triangle. The right triangle ABC blocks the circle. The center of the circle is here at point O, and the radius of this circle is equals to x. Okay, now we'll find out a general formula for a radius of any circle that is blocked by a right triangle. Okay, here we have rule number 1, that a tangent to a circle is perpendicular to the radius drawn to its point of tendency. OM is the radius of this circle that is equal to x, and BC is tangent to the circle at point M. The radius OM is drawn to the point of tendency, that is to say, is drawn to point M, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius MO. That is to say, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. So here point O is the center of the circle. Point N is the point of tendency of tangent AB with this circle. We join points O and N together by a straight line. ON is the radius of this circle that is equal to x. The radius ON is drawn to point N, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. That is to say, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. So inside quadrilateral NOBM we have 1, 2, 3 right angles. And according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees, the missing angle here must be equal to 90 degrees. Therefore, we can relate inside quadrilateral BMON, we have 4 right angles. Therefore, we can relate to quadrilateral BMON as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, OM equals to NB. But OM is x. It is the radius of the circle, therefore NB must be also equal to x. Likewise, in the same rectangle NOMB, NO equals to BM. But NO is x, therefore BM must be also equal to x units in its length. So if we found out that quadrilateral NOMB is not a rectangle but a square, because all of its sides are equal to each other, they are equal to x. In the triangle, the right triangle ABC, side AB equals to A units in its length, side BC equals to B units in its length, and the hypotenuse AC equals to C units in its length. Again, side AB equals to A units in its length, side NB equals to x. Therefore, the length of side AN must be equals to A minus x. Again, A, that is the length of side AB minus x, that is the length of side NB, must be equal to AN. So we can write here that AN equals to A minus x. Again, AN equals to A minus x. A minus x is AN. Therefore, AN equals to A minus x. Here we have rule number 2. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. If we focus on the common external point, point A, from the common external point A, we have two tangents to this circle. We have tangent AN. We have also tangent AS. We have two tangents from point A. tangent AN and tangent AS to this circle, and according to rule number 2, they must be equal to each other. That is to say, AN equals to AS. Again, AN equals to AS according to rule number 2, but AN is A minus X, therefore AS must be also equal to A minus X. Side BC equals to B units in its length, and BM equals to X. So B minus X is MC again. B minus X is MC. Okay. B minus X equals to MC. We'll focus on the common standpoint point C. From the common standpoint point C, we have two tangents to this circle, tangent CM and tangent CS. And according to rule number 2, they must be equal to each other. That is to say, CM equals to CS. But CM equals to B minus X, therefore CS must be also equal to B minus X. Okay, so what is the length? The length of the hypotenuse AC is C. And C in total equals to A minus X plus B minus X. So I'll write it down. The hypotenuse AC is C. And C equals in total to A minus X plus B minus X. Repeat again. The hypotenuse C of the right triangle ABC equals to A minus X plus B minus X. So C equals to A plus B minus 2X. You add 2X to this equation and we get that 2X plus C equals to A plus B. We subtract C from this equation and we get that 2X equals to A plus B minus C. We divide this equation by 2 and finally we get that X equals to A plus B minus C over 2. So we actually found out a general formula for the radius of any circle that is blocked by a right triangle. The radius X of the circle that is blocked by the triangle equals to A plus B, that is the sum of the lengths of the perpendiculars, minus C is the length of the hypotenuse over 2. Again, the radius X of this circle that is blocked by the right triangle ABC equals to A plus B, that is the sum of the side lengths of this right triangle ABC minus the length of the hypotenuse C over 2. Repeat again, the radius X of this circle that is blocked by the right triangle ABC equals to A plus B minus C over 2. Okay. Now we can use the new formula in order to find out the radius of each circle. Okay. We'll focus on the left circle here. The radius we define the radius of this circle as R. The radius R of this circle will be equal to AB, that is 7, plus BC, that is 24, minus the length of the hypotenuse AC, that is 25, over 2. Repeat again, the radius of this circle, the left circle, must be equal to the sum of the lengths of the perpendiculars minus the length of the hypotenuse over 2. 7 plus 24 is 31. 31 minus 25 over 2. 31 minus 25 is 6. And 6 over 2 is 3. So if we found out that the radius of this circle R equals to 3 units. Likewise, we find out the radius of this circle, the right circle that is blocked by the right triangle CDA. The radius R must be equal to 24 plus 7, that is the sum of the side lengths, minus the length of the hypotenuse, that is 25 over 2. So 24, the radius of the right circle equals to 24 plus 7, that is 31. 31 minus 25 over 2. 31 minus 25 is 6. And 6 over 2 is 3. So found out that the radius of this circle, it is also equals to 3 units in its length. According to rule number 1, you have the radius PG, that is known to point G, that is the point of tendency of tangent BC with this circle. Therefore, tangent BC will be perpendicular to the radius GP. That is to say, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. Here, tangent AB is tangent to this circle at point H. We join points P and H together by a straight line. PH is the radius of this circle, that is equal to 3 units. The radius PH is known to point H, that is the point of tendency of tangent AB with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius HP. That is to say, this angle equals to 90 degrees, and this angle equals to 90 degrees according to rule number 1. So inside quadrilateral HPGB, we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. So inside quadrilateral HPGB, we have 4 right angles, therefore we can relate to this quadrilateral HPGB as a rectangle, as we know that the opposite sides of a rectangle are equal to each other. That is to say, PG equals to HB. But PG is 3, therefore HB must be also equal to 3 units in its length. Likewise, in the same rectangle HPGB, HP equals to BG. But HP is 3, therefore BG must be also equal to 3 units in its length. We repeat on the same process on the other side. In this circle, we will have here, we define the point of tendency of tangent AD with this circle as point N. The radius QN is drawn to point N, that is the point of tendency of tangent AD with this circle, and therefore tangent AD will be perpendicular to the radius QN. That is to say, this angle equals to 90 degrees, and this angle equals to 90 degrees according to rule number 1. We define the point of tendency of tangent DC with this circle. This point is point K. We join points Q and K together by a straight line. QK is the radius of this circle, that is equal to 3 units. The radius QK is known to point K, that is the point of tendency of tangent CD with this circle, and therefore tangent CD will be perpendicular to the radius KQ. That is to say, this angle equals to 90 degrees, and this angle equals to 90 degrees according to rule number 1. So inside quadrilateral Q, K, and D, we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. So inside quadrilateral NDQK, we have 4 right angles, and therefore we relate to quadrilateral NDQK as a rectangle. We know that the opposite sides of a rectangle are equal to each other. That is to say, QN equals to KD, but QN is 3, therefore KD must be also equal to 3 units in its length. Likewise, in the same rectangle, QK equals to ND, but QK is 3, therefore ND must be also equal to 3 units in its length. Okay. In the next step, we'll extend the radius HP until it touches side DC. We extended the radius HP by a straight line until it touches side DC of the rectangle ABCD. We define the touching point of the extended HP with side DC as point J. By extended side HP, we created quadrilateral edge JCB. Inside this quadrilateral, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. Therefore, we can relate to quadrilateral edge BCJ as a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, edge B equals to JC, but edge B is 3, therefore JC must be also equal to 3 units in its length. Likewise, in the same rectangle edge JBC, we have side BC must be equal to side edge J. But BC is 24, therefore edge J must be also equal to 24 units in its length. This side edge J must be equal to 24 units in its length. CD or DC is one side of rectangle ABCD, therefore it is absolutely a straight line. If you focus on this side of the straight line DC, as point J, the sum of the angles here must be equal to 180 degrees, according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. Therefore, the missing angle here must be equal to 90 degrees. So this angle equals to 90 degrees. We will extend the radius NQ until it touches side BC of rectangle ABCD. We will define the touching point of the extended NQ with side BC as point L. In this way, we created here quadrilateral NDCL. Inside quadrilateral NDCL, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, quadrilateral NDLC that has 4 right angles must be at least a rectangle, if not a square. So we will relate to quadrilateral NDLC as a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, side ND equals to side LC, but ND is 3, therefore LC must be also equal to 3 units in its length. We define the intersection point here as H So inside quadrangle AJLC we have 1, 2, 3 right angles. Therefore the fourth angle must be also equal to 90 degrees. According to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. So inside quadrangle HJLC we have 4 right angles. Therefore we relate to quadrangle HJLC as a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say LC equals to HJ, but LC is 3, therefore HJ must be also equal to 3 units in its length. In the same rectangle, JC must be equal to HL. But JC is 3, therefore HL must be also equal to 3 units in its length. Okay. So here we have in rectangle NDLC, side NL must be equal to side DL. NL equals to side NL equals to side DC in rectangle NDLC. But DC equals to 7 units, therefore NL must be also equal to 7 units in its length. And again, DC equals to NL, but DC equals to 7 units in its length. It is given as the question. Therefore, NL must be also equal to 7 units in its length. So NL is 7 units. NL, this side NL equals to 7 units in its length. NL minus NQ minus HL must be equal to QH. Repeat again, NL minus NQ minus HL must be equal to the missing side QH. Again, NL minus NQ minus HL must be equal to QH. So QH equals to NL, that is 7, minus NQ, that is 3, minus HL, that is also 3. So 7 minus 3 minus 3 is 1. So finally found out that HQ equals to 1 unit. HQ equals to 1 unit in its length. Or QH equals to 1 unit in its length. Here we have quadrangle AH JD. Inside this quadrangle we have 1, 2, 3, 4 right angles. Therefore we relate to quadrangle AD HJ is a rectangle. Why? Because it has 4 right angles. 1, 2, 3, 4. Therefore, quadrangle ADHJ is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, AD equals to HJ. Therefore, HJ equals to 24 units in its length. Write it down. Side HJ equals to 24 units in its length. HJ equals to 24 units in its length. So HJ minus HP minus HJ minus HP minus HJ must be equal to PH, that is the missing side, 9 segments. Again, HJ minus HP, HJ minus HP minus KJ, Hj minus Hp minus Kj must be equal to the missing side Pk. Hj minus Hp minus Kj must be equal to the missing side Pk. Hj is 24 minus Hp is 3 minus Kj that is also 3. So 24 minus 3 is 21 and 21 minus 3 is 18. So pH equals to 18 units in its length. pH equals to 18 units in its length. So here we extended the radius HP by straight line until it touches the side DC at point J. When you extend a straight line by straight line, the result is a straight line. So Hj is a straight line. And this angle equals to 90 degrees. If we focus on this side of the straight line HP, the missing angle must be equal to 90 degrees. This angle equals to 90 degrees, therefore the missing angle here must be equal to 90 degrees also, according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So inside the quadrilateral PKGL we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. We extended the radius MQ by a straight line, so the result NL is also a straight line. NL is a straight line. If we focus on point K of the straight line NL, the sum of the angles on this side must be equal to 180 degrees. So this angle equals to 90 degrees, therefore the missing angle here must be equal to 90 degrees. According to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So on this side of the straight line NL at point K, the sum of the angles must be equal to 180 degrees. So which angles we have here? We have this angle is equal to 90 degrees, plus the missing angle here, it must be equal to 180 degrees, according to the rule that I mentioned. Therefore, the missing angle here must be equal to 90 degrees. In the next step, we'll implement the Pythagoras theorem on the right triangle QKP. On the right green triangle QKP. So I copy the right green triangle QKP and your page and we'll implement the Pythagoras theorem on this green right triangle QKP. Side QK equals to 1 unit in its length, PK equals to 18 units in its length, this angle equals to 90 degrees. So actually this is the right green triangle QKP that is the common from the original drawing. We implemented the Pythagoras theorem. According to the Pythagoras theorem, PQ squared, that is the line segment that we are looking for. Again, PQ is the line segment that we are looking for. So PQ squared equals to KQ squared plus PK squared. So PQ squared equals to KQ squared. KQ is 1, so KQ squared is 1 squared, that is 1, plus PK squared. PK is 18, therefore PK squared is 18 squared, that is 324. So we found out that PQ squared equals to 324 plus 1 is 325. We take a root of this equation, we get that PQ equals to the square root of 325. 325 equals to 25 times 13. The square root of 25 is 5, so we can take out 25, can take 25 out of the root. And you get that again, the square root of 25 is 5. Inside the root we left only 13. We found out that the distance between the centers of those two circles, that is to say the length of line segment PQ, is equals to 5 times square root of 13 units. The distance PQ, that is the distance between the centers of those two circles, is equals to either 5 times square root of 13 units, or in terms of numbers, is equals to 18.03 units. Okay, I repeat again on the answer to the question. It's that the distance between the centers of those two circles, that is to say the length of line segment QP, is equals to either 5 times square root of 13 units, or in terms of numbers, QP equals to 18.03 units. And that is the answer to the question. In the next step, I'll summarize the lecture. So in this lecture we found out the distance between the centers of those two circles. The center of this circle is here at point Q, the center of this circle is here at point P, and we found out the distance between those two centers, that is to say the length of line segment QP. In addition, we know that those two circles are located inside rectangle ABCD. And we also know that the width of this rectangle, ABCD, is 7 units, and the length of this rectangle is equals to, BC equals to 24 units. Again, our mission is to find out the distance between the centers of those two circles, that is to say the length of line segment QP. So first of all, because of the fact that ABCD is a rectangle, it means that all the 4 angles inside this rectangle, they are right angles. So those 4 angles, they are all right angles. That is to say, each of them is equal to 90 degrees in its size. So those 4 angles, they are all right angles. And because of the fact that this angle equals 90 degrees, it means that triangle ABC is a right triangle. Therefore, we can implement the Pythagoras theorem on this right triangle ABC. According to the Pythagoras theorem, In this right triangle ABC, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, AC square equals to AB square plus BC square. Repeat again. In the right triangle ABC, according to the Pythagoras theorem, by PT is the abbreviation for Pythagoras theorem, AC square equals to AB square plus BC square. So AC square equals to AB square. AB is 7, therefore AB square is 7 squared, that is 49, plus BC square. BC equals to 24 units according to what is given in the question, therefore BC square is 24 squared, that is 576. So in total AC square equals to 49 plus 576 is 625. So AC square equals to 625. We took a root out of this equation and finally found out that AC equals to the square root of 625. This is actually 25. So the length of the hypotenuse AC of the right triangle ABC is 25 units. Okay, then we actually proved that the general formula for a radius of a circle that is blocked by right triangle, we actually proved that the general formula for the radius of a circle that is blocked by a right triangle, if the radius of this circle is x, then x equals to a plus b minus c over 2. A is the length of side AB of the right triangle ABC, b is the length of side BC of the right triangle ABC, and c is the length of the hypotenuse AC of this right triangle ABC. So it is a plus b minus c over 2. That is the length of the hypotenuse, that is the length of this, the radius of this circle, x. Again, according to our definition, the radius of this circle is x, and therefore the value of x must be equal to a plus b minus c over 2. So we proved that this equation is true. We actually used there two rules. Rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. OM is the radius of this circle that is equal to x according to our definition. The radius OM is drawn to point M, that is the point of tendency of tangent BC with this circle. That whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius MO. If BC is perpendicular to MO, it means that this angle equals 90 degrees and this angle equals 90 degrees according to rule number 1. Likewise, this angle ABC equals to 90 degrees because triangle ABC is a right triangle. ON is the radius of this circle that is equal to x according to our definition. The radius ON is drawn to point N, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. If AB is perpendicular to NO, it means that this angle equals 90 degrees and this angle equals 90 degrees. So inside quadrilateral NOBM, we have 1, 2, 3 right angles, therefore the fourth angle must be equal to 90 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore inside quadrilateral NOBM we have 4 right angles, therefore we can relate to quadrilateral NOBM as a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say OM equals to NB, but OM is x, therefore NB must be also equal to x. Likewise, according to the same rule, that the opposite sides of a rectangle are equal to each other, we get that NO equals to BM. But NO is x, therefore BM must be also equal to x. So we actually found out that quadrilateral NOBM is not a rectangle but a square. Why? Because all of its sides are equal to each other, they are equal to x. Okay? So if NB is x and AB is A, then AB minus NB must be equal to AN. AB is A, NB is x. Therefore A minus x must be equal to AN. Again, A minus x equals to AN. Therefore, an equals to a minus x. Okay. Here we have rule number 2. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. We have the common external point, point A. From the common external point, point A, we have two tangents to this circle. Tangent AN and tangent AS. And according to rule number 2, they are equal to each other. That is to say, AN equals to AS. But AN is A minus X, therefore AES must be also equal to A minus X. Likewise, we know that BM equals to X. BC equals to B. Therefore, BC minus BM equals to MC. Again, BC, that is B, minus BM, that is X, must be equal to MC. Therefore, in total, MC equals to B minus X. B minus X is MC. So, MC equals to B minus X. We'll focus on the common external point, point C. From the common external point, point C, we have two tangents to the circle, tangent CM and tangent CS. And according to rule number 2, they must be equal to each other. That is to say, CM equals to CS. But CM is B minus X, therefore CS must be also equal to B minus X. So, what is the length? The length of the hypotenuse AC is C. C in total equals to A minus X plus B minus X. Again, C, the hypotenuse C of the right triangle ABC equals to AS plus SC. AS is A minus X and AC is B minus X. So in total, the hypotenuse C equals to A minus X plus B minus X. Okay, again, the length of the hypotenuse C is A minus X plus B minus X. That is to say, C equals to A plus B minus 2x. Okay, here we added 2x to this equation and we got the 2x plus C equals to A plus B. We subtracted 3 from this equation and found out that 2x equals to A plus B minus C. We divided this equation by 2 and finally found out that x equals to A plus B minus C over 2. And that is actually a general formula to find the radius of any circle that is blocked by a right triangle. That is to say, the radius of this circle that is blocked by this triangle ABC must be equal to A plus B minus C over 2. Okay. Now we will use the general formula to find out what the eye of this circle and the right circle here. According to the formula that we have, x equals to A plus B minus C over 2. AB equals to 7, BC equals to 24, and the hypotenuse AC is 25. So it is 7 plus 24 minus 25 over 2. The radius of this circle must be equal to 7 plus 25 minus 7 plus 24 minus 25 over 2. 7 plus 24 is 31 minus 25 over 2. 31 minus 25 is 6 and 6 over 2 is 3. So we found out that the radius of this circle R equals to 3 units in its length. We repeat it on the same process on this circle that is blocked by the right triangle CDA. The radius of this circle must be equal to 7 plus 24 minus 25 over 2. 24 plus 7, that is 31, minus 25 over 2. 31 minus 25 is 6, and 6 over 2 is 3. So actually found out that the radius of this circle also equals to 3 units in its length. Okay, then we extended the radius NQ by straight line until it touches the circle at point L. We also extended the radius HP until it touches the circle at point J. So here we have this angle equals to 90 degrees, therefore BC is a straight line, therefore the missing angle here must be equal to 90 degrees. Likewise, this is a straight line, this angle equals to 90 degrees, therefore the missing angle here must be equal to 90 degrees. The same thing is true here. In the quadrangle N and D, CL, we have 1, 2, 3 right angles, therefore the fourth angle must be equal to 90 degrees. Therefore the missing angle here must be equal to 90 degrees. So inside quadrangle PGLK, we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. And here we have 1, 2, 3 right angles, therefore here we have in quadrangle HB, CJ, we have 1, 2, 3, therefore the fourth angle must be also equal to 90 degrees. So in quadrangle KL, CJ, we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. The same thing is true inside quadrangle PGLK, we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. NL is a straight line, so this angle equals to 90 degrees, therefore the missing angle must be also equal to 90 degrees. Therefore the green triangle QPK is a right angle because this angle equals to 90 degrees. Inside quadrangle ADJH, we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. Therefore quadrangle ADHJ, here we have 4 right angles, therefore quadrangle ADHJ is a rectangle. We know that the opposite sides of a rectangle are equal to each other, that is to say AD equals to HJ. But AD is 24, therefore HJ must be also equal to 24. So HJ minus HP, that is 3, minus KJ, that is also 3, must be equal to the missing side, PK. Therefore PK equals to 24 minus 3, that is 21. 21 minus 3 is 18. So PK equals to 18 units in itself. And we have here quadrangle NDLC. We have inside this quadrangle 1, 2, 3, 4 right angles. Therefore we relate to quadrangle NDCL as a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say DC equals to NL. But DC is 7, therefore NL must be also equal to 7 units in its length. So the missing side here, QK, must be equal to NL, that is 7, minus NQ, that is 3, minus KL, that is 3. So in total, QK must be equal to 7 minus 3 minus 3, that is 1, and PK equals to 18. Now we can implement the Pythagoras theorem on the green right triangle PKQ. This is the right triangle PKQ that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle PKQ, PQ square equals to KQ square plus PK square. So PQ square equals to KQ square. KQ is 1, therefore KQ square is 1 square, that is 1, plus PK square. PK is 18, therefore PK square is 18 square, that is 324. So in total PQ square, that is the square of the hypotenuse, equals to 324 plus 1, that is 325. So PQ square equals to 325. We took out all of this equation and finally found out that PQ equals to the square root of 325. 325 is 25 times 13. The square root of 25 is 5, so I can take out 25 from the root. Again, the square root of 25 is 5. So inside the root we left only with 13. In conclusion, we found out that the distance between the centers of the two circles, that is to say PQ, equals to either 5 times square root of 13 units, or in terms of numbers, this equals to 18.03 units. I repeat again, the distance between the centers of the two circles, that is to say QP equals to either 5 times square root of 13 units, or in terms of numbers, QP equals to 18.03 units. Okay, thank you very much.